Greetings, ladies and gentlemen. Welcome to our next episode of AEC Automation Success Stories. I'm your host for today, Yashar Moradi from Bimondis, and I'm very pleased to be able to introduce to you Milos and his huge projects. To give you a general feeling, the agenda is that we do a round of introduction to ourselves and our companies. Then we jump directly in the presentation from Milos, which is Coding the Giants, and goes mainly on how to use digitalization and programming for making construction projects more efficient. And afterwards, we go into a round of Q&A, and feel free to basically send your questions in the comment section below, and we basically read them one by one after the presentation. So to give you a brief introduction, my name is Yashar. I'm co-founder and CTO at Bimondis. To give you a little bit of background, I'm a software developer for the past 29 years and a civil engineer, and with a sweet spot for GIS and AEC, and been busy doing software development for the past 2 decades or more for companies like Navis, like Claudio, like Scoperty. And we started Bimondis because we believe that the construction industry needs a little bit of push to go into the right digitalization modus, because what we see is that the construction industry is way behind other industries, and we want to fix this or support fixing this with all the other experts which are working in this domain, and we think that the potential is still untapped, and we think that we have to start with people, and people should basically enable the industry to do this digital transformation. But today is not about marketing for Bimondis. You can take a look at the website if you want, but our talk today is about what our very valued guest does, Milos Dimcic. He's basically has been 15 years or more than 15 years in the industry, architecture, structural engineering, and programming. Basically, a very unique and interesting merge of different disciplines. And he started something called programming architecture in 2011, and is working with a lot of very famous names like Foster and Partners, Zaha Hadid, Strabag, and so forth. And I think more to his background and his company, we can hear from himself. So welcome on board, Milos. Thank you for accepting our invitation.
Thank you for inviting me.
So can you tell us? Sure, please.
Okay, sure. I introduce myself, and then I'll share my screen. So as Yashar told you, that's basically summed up. Like, I'm originally an architect. That's maybe an interesting thing. And I went into programming after I finished the Faculty of Architecture, which might be interesting for some of you, that we didn't study computer science, right? And then after my PhD, I did open my company, and I worked on a lot of different projects that spanned the last 15 years or so. And basically what I will show you is a slight overview of some of the projects. Of course, many of them I will not show, but maybe some of them that are interesting. I will not go into the detail because we don't have time, because for every project it could be a 2-hour lecture. And for some of them, I will not go into detail because this is more of a public show and I cannot show a lot of it publicly, a lot of the details. But I think it will more than enough to give you an overview of basically what programming can do in the building industry, right? How can it help? What can it automate? Maybe give you some ideas and show you that it doesn't have to do with just complex geometry, complex architecture, that it actually has a application in a lot of different types of architecture. So I guess I could start sharing my screen, Yasha, or
Sure.
let's
Yeah.
see how
Thank
that
you. Thank
works.
you. Let's go into the demo. So you're up.
Okay. Okay, so let's start like this. This is where I come from. So 2006 is the year I finished architecture, and between 2006 and 2011, this transition to programming is happening. While I'm doing my PhD, which you can see on the right side, which my PhD was a structural optimization of free-form grid structures, where I had to basically create a plugin for Rhino that connected Rhino with the static analysis software. And then I generated thousands or millions of different grid structure solutions and tried to find new ways of optimizing them, statically analyzing them, getting the result, using genetic algorithms and so on. Again, a 2-hour lecture that we're not going to go into. And in parallel with this programming that is happening for my PhD, I'm working for Knippers Helbig structural engineering office in Stuttgart on this kind of projects that you see on the picture. So it's free-form grid structures where you have to do a lot of programming because every single element there is unique. There is a lots of production problems, static optimization problems, and that's how I got it first into Rhino scripting and then later into more complex programming. So one of the first projects while I was still working in the Knippers Helbig office that was where the programming was heavily needed was this airport that we did with Fuxas. We won the competition with him then. This is pre-Grasshopper 2007. This is still Rhino script. And I basically wrote a script that generated this entire facade and the structure in between automatically. This was the largest freeform surface in the world at the moment then. 300,000 square meters of freeform surface. You have two shells outside and inside, and in between a large structure that you can't see at the moment. And each of these hexagons that you see on the top right was fairly big. One hexagon was like 4.5 by 3.5 meters. And the hexagons themselves were three-dimensionals, which you can slightly see. And they were populated over a double curved surface. And the task was first have different types of hexagons. So you can see on the top down left like Excel tables. We basically got like brush strokes from Fuxas where he wants different types of hexagons with different types of openings. We transformed those brush strokes into Excel tables, and those Excel tables then automatically went into a script, and the script generated all the hexagons and made sure that all the glass elements were flat. So that was a bit of a challenge, a 3D structure over a double curved surface. Anyway, this all worked out. What you see here is not a rendering. These are real pictures from the real airport. Some of you might have been there. And this, because I basically single-handedly programmed this, and every week we got new surfaces from Fuxas, and every week we had to regenerate everything. I was convinced in the power of programming, the power of automation. I thought if like a single person can handle the largest freeform structure in the world, regenerating facade, regenerating structure, this has to be the future. So this made me start my own company in 2011, right after I finished my PhD. And I decided, okay, I'm going to try to bring automation into these three areas, these three phases of the project, if you want. It's design, engineering, and fabrication, eventually an assembly. And the goal was from the beginning to try to automate each one of these separate phases, but then introduce the integration, because that is kind of what we all are striving to, right? We all talk about how our industry is siloed, everybody is creating their own models, and then the communication between the models does not work, and so on. Well, if you use automation from the very beginning, then you can actually do that. So in the last 15 years, developed a system. I showed this graph on LinkedIn recently. This does not mean that I work primarily in Revit. I actually work primarily in Rhino, and most of the projects you will see are done almost entirely in Rhino without any need for any other software. But in the least recent years, I'm working more toward this integration. And so I'm trying to connect different software in the code, so that the idea is that you can create very, very, very simple wireframe models of whatever you're building, and then from that wireframe model, automate and extract anything you need. Automate a full Revit model, automate a structural model, CNC files, and so on and so on. I hope that what I will show you will maybe demonstrate some of those things. From very early days, I tried to enter the design phase, and this shows one of the very early projects where I created a small plugin for Rhino, where we used the sliders to try out different structural solutions, like very fast. And what you don't see here is that all of these solutions that are tried out were then exported to a static analysis program at the click of a button, so that we could test and try different solutions. And then I found that really interesting, and I thought that would be the future of what I will do in the next 10 years. I was then surprised that I didn't do much of it. Although I did do some of the work in the design phase, let's say the design exploration. This is another simple example of some small pavilions that we did, where I used some natural grid structures that I developed in my PhD. I did find myself working almost entirely outside of the design phase. So most of the automation I did came after the design was already done. And I'm trying to get back to the design, but maybe I'll address that at the end of this lecture. So what happens after the design is done? So after the design is done, after the architects are done, they usually develop the building until a certain level of detail, right? Let's say 100, 200, and so on. They don't go very much, like depending on the architectural office, but that's approximately it. And then someone, usually a general contractor, takes over the model and then has to develop everything until the last detail, prepare it for publication, assemble it, build it, and so on. And so that's where I came in these kind of phases where everything has to be generated. And I worked on many, many buildings, but I will show you a couple of examples. This is an example of the Bloomberg building in London, Foster and Partners. I worked with Zele, who made a lot of steel elements that are behind, that you cannot see, especially here where the spiral stairs are. And the interesting part there is that you basically had to generate all this kind of 3D steel structure, but the input here was a single curve. So the input was a single curve, and then like a PDF file with a lot of explanations and details and so on. But basically, all of this that you see on the screen was generated automatically literally at the click of a button, where the single curve was an input, right? And then afterwards, when we generated the 3D, we had to generate 2D as well. This is, I'm talking 2013 or 14 or something like that. And this was all done in Rhino. So at the click of the second button, let's say the 2D was generated. And then all these outlines were automatically ready for production, right, for the CNC file. But then, because we didn't know who will produce what kind of CNC files they need, we had to also generate these kind of old-fashioned shop drawings, right, with all these dimensions and so on, so that someone can manually read it and produce it. And then I showed this slide where it says that no human draw a single line here, just to emphasize the level of automation you can achieve. So we generated at the end of, let's say, 1,200 or something like that, drawings like this, where literally none of the lines were drawn by a human. It's all automated. The human just like checked out at the end if like the layout is okay, or spend maybe 2-3 minutes per drawing to see if some dimensions overlap or something like that. And the point was that we didn't like doing this because the point of automation is to generate CNC files, as you will see a bit later, that go straightly to the machine. But even on this way there, you can automate a lot of stuff as a middle solution. This is a Kuwait International Airport that we worked with Zobek. It's Foster and Partners, but we worked with Werner Zobek, who did structural engineering. And I can't show you a lot of details because the project is still in construction. But why I show this slide is because when people think about parametric design, programming, and architecture, and so on, they mostly imagine some kind of a steel structure, wooden facade. They don't think about all the things you can do with programming. And this slide shows the scale of this airport. It's 1.2 kilometers from left to right there. And it had like, I forgot now, like 40, 50,000 of concrete panels, each one 3 by 3 meters. And what we did here is we generated reinforcement. So for all these concrete panels throughout the entire airport, all 40, 50,000 of them, we automatically generated reinforcement in reinforcement plans that we used to create them. So anything in the building is geometry, and geometry can be generated automatically. So you shouldn't limit your thinking when it comes to parametric design to some grid structures and so on. But as you can see, a reinforcement is also a possibility, even for normal projects, as you will see. What's interesting is that you can do a lot of things, a lot of optimization when you connect different software. And this is an example of the Schuko parametric facade. It's a project we did with Engelsman Peters, also 6-7 years ago. And the Schuko developed this parametric system where they actually allowed architects to take these points that are outside. So in this particular facade type, you see these 2 points that are outside of the facade. And you as an architect are free to take those 2 points and move them around as you wish. And if you want, create all unique facade elements, but Schuko will basically produce it for you for the price as if they were all the same. So that was the idea, and there were many different types. This is just one, there were 14 different types with one single point on the outside, 4 points, and so on, triangular ones and so on. But the question then became, how do you do static analysis with it, right? Like, how do you know what's the worst case solution? What's the best case solution? How do you dimension this if you actually let people and architects play with that? So there we connected again the Rhino with the static analysis software. We did this first with Oasis, GSA, later with Luba, with RFM and RStab. And as you can see here, we generated 4 or 6 solutions per second. That means that the geometries were generated, they were prepared for static analysis, and then statically analyzed, and then evaluated, and so on. And so we could then determine for each type, facade element, what is the best case, what is the worst case, and maybe use some dimensioning, right? Know how to dimension the profile so that they work for any case that the architect can come up with. That was one type of the problem. And then we went further. We solved the different problems, but one that is interesting is that once you do the dimensioning, once you take a certain profile, let's say you know that the profile 80 millimeters will cover all the solutions, then the question is, what if I take the profiles of 60 millimeters? What solutions can I cover with 60 millimeters, right? So then what we did is, I think I'll show you just in a second. Yeah. Then we could analyze, and then we could say, okay, for a 60 millimeter profile, you get this green cloud, right? So you as an architect, if you want a bit cheaper, a bit lighter facade element, you can move within this green cloud. If you want a 50 millimeter, then this cloud is going to be even smaller. So we basically created a catalog of different solutions. So that's one of the examples what you can do if you connect different software and then do geometrical and statical optimization. A similar thing you can see here in the Apple Store glass stair study, also with Engelsman Peters and Zelle, also a long time ago, let's say 5-6 years ago, maybe 7, where the Zelle is doing this, engineering this Apple Store glass stairs. And the question there was also the creation of different models, right? So you have a model, you have new stairs that come, always slightly different. They're not really the same. And then the structural engineer has to create their own model from scratch. They told us usually it takes them 8 weeks or something like that. And then you have to create a model for production and so on. So we said, okay, why don't we combine all of that into one single model? And so with a small plugin, we could move the sliders around, create these geometries. And once we're done, with a click on a single button, we could export that to the structural analysis program, and also to prepare everything for production. So that was also one of the early examples of this integration, right? Connecting different elements. Similar task with the Chatstone Mall in Melbourne, when we got, this was, I think, also with Engels and Peters then, with Zele. When we got to work on this, the Engels and Peters had to do a glass static analysis for all these elements. And they told me usually they estimate which is the best case, which is the worst case glass panel. They do a detailed static analysis on it, and then they extrapolate over all of them. We're talking about 3,000 plus unique glass panels, right? And then I said, okay, why don't we use our tools? Why don't we create a plugin that will do a detailed static analysis in a loop for all 3,000 panels? So that's what we did, and we actually analyzed all of them, and we could, of course, we realized that the human estimation of which one is the worst case, which one is the best case was not right. We found different ones that were worst and best case. And in this case, in this particular project, all the glass panels, I think, were still done with the same thickness, but you can imagine that you can start then optimizing the thickness of the glass panel, the type of the glass panel, and so on. What we did recently on this Madison Square Garden in Las Vegas is something that's like, I cannot go into too many details. I will try to explain what we did in a less public setting. I could show maybe some of the tools that we developed, but I hope I'll get the point across. It's a $2.8 billion project, and the interesting part you have to keep in mind is that there's a small group of people working on it, the Zele, the engineering, and we did the automation of the structure. And you hear some sound, right? This is from the U2. This is from the U2 concert, which was happening inside the Sphere at the opening. And our task was, we were mostly concerned with this inner shell, right? We were mostly concerned with this inner shell because the outer shell was relatively simple. As you can see, it's just a simple grid structure. It's just literally a shell. But the inner one had was pretty complex, and it had multiple layers, right? So we're talking about approximate the diameter of 120 meters, and we are talking about the primary steel structure that underneath holds a secondary aluminum structure that holds the tertiary aluminum structure, and then the tertiary holds the LED screens. And the LED screens cannot have a gap between them. So anything that's above 0.5 millimeters can be perceived by the audience as the black line. And the screens themselves were very small. They were like half a meter by 30 centimeters. They were like, I don't know, 15,000 screens connected together. So they had to work in a very precise setting. They had to work there in the exact temperature of 23 degrees, I think, because of the temperature dilatation. But that shows you that how precise the engineering had to be done. So it had to be automated. And although we are talking about a sphere, a fairly regular shape, there were a lot of things like the position of speakers and so on that made the geometry highly irregular. So what you see here is this 885 facets, so-called, and each one of them is like 5 by 5 meters approximately, and almost all of them are different. So that we had some symmetry left and right, but if you look at one half of the sphere, all of them are different on that half. And when we created everything, generated everything, because everything was automated, we didn't care. We treated every facet as if it was different. Because once you create automating stuff, at some point you don't care if all the elements are the same or if all the elements are different. It's just you're doing the same thing. The algorithm is doing its thing. You're just creating modules in algorithms, but you don't care about geometry. So basically, we treated everything as different, and you have to remember, without me showing any details now, that this was a machine, basically. This is a big TV, right? So it was full of cables and holes, and it's a very complicated structure, and Zela did a marvelous engineering there. But the question was, so what did we generate? So we generated these layers of structure, right? And the layers of structure are made out of structural members like steel, aluminum, and so on. So what we ended up with is 30,000 or so unique aluminum profiles. And we're talking about aluminum profiles that are like 5-6 meters long. And because of these cables and connections, each profile had more than 100 works. By work, I mean the machine work, like is either a drill or a thread or a pocket or something like that. So it was every profile was a Swiss cheese in itself, and it had to be connected with all the other profiles in the scheme. And we started with very, very basic rectangles. You see on the bottom here. Here you see these very, very basic rectangles of these facets. That's what we started. That's what we took as an input, and then we tried to generate everything else automatically as an output. So we generated 3D profiles, like the ones you see here, for example. And once we generated them, then became the question of production came, right? So how do we produce them? Well, we exported them all automatically into some 3D files, into some step files, right? We exported 30,000 step files, and they go into the machine, right? Easy. Not really easy, because the software that you use to create, to produce something, there is a software that translates step files into machine files, right? G-code. And if you have complex profiles with like 100 and so works, that doesn't always work, and you have to manually adjust it and so on. And with such a huge number, that can be a bit problematic. So again, programming came to the rescue. And we first agreed on which machines will be used to produce this. These are aluminum machines that use this NCW standard, which is a G-code standard for aluminum profile machines. So what we did is we created an NCV exporter directly in Rhino, like from scratch. So once we generated these 30,000 step files, we then automatically also generated 30,000 NCW files, right? And if you open an NCW file, this is what you see. Here's on the left. It's a normal G-code file, nothing special there, but it was created uniquely, right, for every profile, right? So for every single work there, drill, notch, mill, pocket, everything was there. So that once you get to the machine, you shouldn't have any problems, right? And all the errors, of course, you cannot avoid some errors happening along the way. And all the errors we did find was at the profiles where someone had to manually intervene, right? So everything that was fully automated, no problem there. Wherever a human had to maybe change some drill, move it by 5 millimeters or 10 millimeters, that's where the errors happen. So we realized that automation is saving a lot of work, especially because around 30 or 40% of the code is error checking, right? So we had routines or algorithms that overlapped the NCW file and step file and tried to see if they fit together, if there are errors, and so on. So we had a lot of error checking code that automates the human work in that area as well, which is pretty cool. And again, with this structural niche of ours, again, to show you the details, so that you can just show you an overview of how we do it in general. We created this complete structural model, like for structural analysis, and we had at the end close to or even more than 200,000 structural members. So you can forget about doing anything manually there. And how do we do that? Well, we create this geometry in Rhino, and the whole project from these small rectangles that you see on the top left until the CNC machine and the produced element. Everything was done in Rhino, right? No Revit, no ArchiCAD, no Tekla, no, just Rhino and Excel from time to time, because all the elements in our models have all the attributes they need. Every single screw, every single assembly has all the color, coating, mass, whatever. There are 55 properties. And so you can extract everything you need at the click of a button, like all the part lists, all the bill of quantities. You don't have to do any of those manually. Just click a button and you have the exact number of screws per facet, per hemisphere, whatever you need. You have the weights of all screws, of all members, and so on. But when it comes to structural analysis, as you know from experience, the engineers usually do their own model. But in our case, we didn't have to do that. We used the same wireframe model that we used to create 3D elements for production. We used the same one and did some changes in the code to create a structural model. That means that every line in our model and every point got these specific properties that are specific for the FM's finite element method software, right? You can see here on the left, for example, every member knew what the nodes, which node it has at the start, which node at the end. This CS start means cross section at start, cross section at end, what hinge it has, what eccentricity it has, and so on. And then on the right, you can see like every point, every node knew its number, which members are connected to it, what is ID, what type of it, and maybe if it has a load on itself, you can see load Z, and so on and so on. So we were able then at the click of a button to export that to a static analysis software, and in this case RFM and RSTAB, using code. This is just a small snippet so that you see how that looked like. You set the loads, load combination, hinges, cross-section support, and then you don't export DWG or DXF or I don't know, and then they have to import it and set stuff manually. No, we export the actual RF6 or RS9 or whatever file, and when they open it in their RFM, everything is there, everything. They just have to click on analyze, right? All the loads combinations, support, literally, they don't have to do anything. So that's the idea of completely integrating everything and creating these models from scratch. This is the hospital in Jerusalem that we finished recently. It opened a couple of months ago. And we did a similar thing, this time with VHAG in Austria that produced all these timber elements. And it's very nice when you can create basically this full digital twin model, right? If you have this model where you zoom in and you see every steel detail, like you see here down on the right, and you can see every screw, and then you can click on the screw and then see all the properties of the screw, which it is exactly, how many pieces of it is there, what's the weight of it, what's the color of it, and so on. And if you can create this entire model, then you avoid a lot of errors in production, right? And a lot of people think they cannot do this because, first of all, the model will be too heavy, or who has time to model all this and so on. And that's exactly the point of automation, right? If you automate everything, you start with this simple wireframe, then you can generate what you need when you need it, right? I don't hold all the screws all the time in the entire model. I hold just the position of the screws, and all the beams, I hold just the position of the beams or the axis of the beams, and then I generate what I need, when I'm ready to export the model, when I'm ready to count all the screws or the weights of the beams and so on. Then at the click of a button, I can extract what I need. And then I can do some things that are not usual. For example, here on the left, you see container packing, right? Because things that were produced in Austria had to be shipped to Jerusalem. So we created this optimization of dividing these beams into the maximum size that can fit in the container. These are the beams in the interior, by the way. I didn't describe the project. This is the outer facade that you see, made out of wood, but the entire interior as well was made out of wood. The Faro architects did that from Canada, and they're very famous for these types of building. They have lots of these wooden buildings. And yeah, we optimized the container packing, but on the right, when it comes to these classical installation plans, workshop plans that are needed to produce the wood elements, you can automate them as well, and that's what we did. And as you can see, I showed you reinforced concrete, I showed you steel, I showed you aluminum, I showed you timber. Automation is all about geometry, and geometry is material agnostic, right? It doesn't matter what type of projects you're building, what material. Automation can always help with the geometry generation. And here is just, you can see a couple of interesting pictures from the construction. You see what kind of cool elements we had, like this curved one at the corner, which is basically a 3D sculpture made in timber. And on the right, you can see also a small snippet of how the model actually looks. So every nail, every screw is there. And once we go into the production, that help us to track and design everything. And right now I'm doing a research project with Strabag that deals with concrete printing. And that's again another case of the variety you can achieve using programming. Here we are creating some kind of a plugin that basically can import Revit walls or Revit slabs or whatever. We're concentrated on walls at the moment. And from this Revit wall geometry, connected directly to Rhino. In Rhino, we have algorithms that create a path. We have different kind of parameters that we can move along, the sliders that we can move left and right to optimize that path. And using that path, we extract the G code, and the G code directly goes to the robot arm, and the robot arm can print walls on the site. This is a research project, but of course, Strabag is a very big company, so they're already doing some testing, and it's pretty cool, but there's not much I can show from my side yet. The people on the Strabag side are doing most of the physical experiments. I'm doing the code. And there's a lot of it that I don't show here that you can do with code, and especially in the design phase, and that I did in the early days, which is like analyze the sign, analyze the shadows. These are some screenshots that we did actually not for architects, but for an electrical engineer who created some kind of a solar panel farm where the solar panels were rotating. So we did like different kind of shadow analysis where like I could extract the volume of the shadow, look if it intersects something and so on. Not gonna go into detail about that, but for some early projects, I created a rain plugin for Rhino where I could actually visually look at the raindrops fall and visualize the path of the water and so on. And so these are all kind of little tools that you can do using automation. And I try to, in my practice, I try to spread as much as I can because I believe in this integration. So if someone is interested in the technical aspects, I started programming in C++ in the first 5 years. Then I moved to C# because it was much easier. And so especially because it was much easier to connect with other software, because other software like Revit, Tekla, RFM, and so on, they give you this C# API, so you can connect them in one routine. However, I really like to experiment with other types of software. I love the Unreal Engine and see how we can connect all these to create superb visualizations. I'm experimenting with AI, and for that you have to use different kind of software. And since we are aware that everything is moving to the cloud, like all the tools for collaboration are moving to the cloud, we cannot lag behind. So I personally had to learn a lot about JavaScript, HTML, CSS, and so on, so I can see how I can contribute in that part. I even have some videos on my YouTube where I talk about Rhino Compute and other systems that can help you create things in the browser that will then use geometry calculations in the background and so on. But that's not the subject of this webinar. The subject is basically to show you an overview of what automation can do, and the important point, which is a bit hard to grasp after this presentation maybe, is that you don't have to have a $3 billion project, or you don't have to have a free-form double-curved surface in order to apply programming, right? So there is a lot of standardization and automation that you can apply in normal standard apartment buildings, right? Why? Because even in normal standard apartment buildings, the MEP engineer, the structural engineer, the architect, they all create their own models and they cannot communicate with each other. But if you start with a very simple wireframe model, if your wall is just a rectangle, if your slab is just a rectangle, if your column is just a line, once you have this wireframe and you can start using automation tools, then you can do what? You can do this, what I listed here, like which the industry still does manually, right? You take that wireframe model, click the button, suddenly you can create this full 3D digital twin. And in order to do that, you need to solve connections, right? That's not easy. Like a beam and a column, they have a connection between them. But all of that can be solved automatically, like with an algorithm. So then you can extract 2D workshop drawings, installation plans, create full FM models, and I didn't list here the MEP stuff, installation stuff, and so on, but that also goes without saying. And what you saw from a real example, you can create production-ready CNC files. So you can span this whole process from the design until the very fabrication, proverbially at the click of a button. Of course, there is a couple of more clicks of the button there, but you can create your Excel tables, procurement, and everything you need by using automation. So yeah, I will stop there because I think I did approximately a half an hour, maybe 1 or 2 minutes more, and I will be yeah, generally open for questions. But as I said, this was a very, very, very brief overview since you saw the projects. Every project can go into much, much more detail, and I would be able to show a lot of more interesting algorithms. So thanks.
Thank you, Milos. It was really impressive. Can you stop sharing?
Yeah, sure. Just
Thank
a sec.
you.
Yeah.
So very impressive indeed. And once you see what is possible, you can't go back to do everything manually, and
Yeah.
that's exactly what in my opinion as well is missing in the industry. We think about digitalization, we talk about digital transformation the whole time, since I can remember, and what we achieve is basically storing and archiving everything yet in another format, and just do everything clicking through manually and 100 times and do the repetitive tasks by ourselves. But we forget that this digitalization, having everything in digital format, is just a prerequisite for everything else that happens afterwards.
Yeah.
And since we already have everything now in digital format, or for most of the larger projects, it is pretty easy to start with baby steps, just to automate the repetitive tasks. It doesn't have to be a Las Vegas sphere, but you can start by, I don't know, search on replacing doors and windows.
Yeah.
Or
create different views in Revit or plans
exactly,
in Revit.
exactly. Create different views and plans. Create annotation, automate annotation. These are stuff that everybody can do even without knowing programming. With especially these days with graphical user interfaces and visual programming interfaces like Dynamo. You can basically just put two nodes, connect them together, and say everything that has this property, change it to that property, and you don't have to go and hire I don't know 10 working students and let them change the properties for you, because a provider cannot provide what you ordered. And of course, for me, working without programming doesn't make any sense. And what I also loved about your presentation was this integrated model concept. I know why civil engineers do what they do, and I know why the architects and civil engineers work in two different silos historically, but I don't understand why they do it still.
Yeah.
Because back then you had an architecture plan which was mostly 2D, mostly on paper, sometimes in CAD format, and you had to basically start defining your nodes and elements. But right now with 3D modeling and everything in digital format, that's the way to go.
Yeah.
And also the logistic optimization. I think that's a really good addition for especially for prefab construction.
Yeah.
Because if you're moving larger elements and larger modules, then it really needs to be optimized. How to package them, how to send them, what are the distances, how is the CO2 footprint of transportation even. Yeah.
Yeah, exactly. I mean, so whenever you design or do whatever you do into this design process, in these design phases, everybody that does that notices patterns, notices rules, because humans, when they do that, they follow rules, right? If a human was supposed to make those container plans, they would say, okay, I have to divide the beams so that the maximum is 13 meters because I can't fit more, right? And then you would start dividing them. That's a rule, right? And then you say, okay, I think I have to put the heavier one down, and lose those little spaces. So while you're doing it, you're following rules that could be programmed into a machine, right? And most of the things you do when you design in different phases, when you self-inspect, you're following some rules that actually can be programmed and used to automate. Even when you create plan views or whatever facade, you say I have to create one from the front of the building, one from the back of. So again, you're following rules that could be programmed, and then you can click a button and you can create automatically the views or whatever. It's just that I think that people have to, realize or think about more in the direction of what can be automated. Maybe it's too much out of the reach or out of their head so that they can think about it. I don't know.
Exactly. We're open for any questions that you have. So if you have any questions, please enter them in the comment section. And until then, we can I can actually show you where you can start with this automation. I try to keep it with less marketing, but generally what we discovered in our industry is that exactly this starting point, this entry barrier is perceived too high. It is not high at all, but it is perceived too high because everybody was busy doing what they did, and first came CAD, then came BIM, then we slept on BIM for 15 years and still fighting which BIM standard, IFC versus I don't know, and level of details, and basically we make it so impossible to move for everybody. And that's why we basically started the AEC Automation Coding School. And basically, like I said, I don't want to do any marketing here, but these are the 3 tracks that we are preparing trainings for. Automation series is basically for everybody who uses any BIM or architectural environment and basically want to learn what they can automate, how to automate, and why should they automate. Coding series is a little bit more hardcore, writing plugins, writing add-ons, working with IFC.js, creating web interfaces, and so forth. And the data series is where you learn how to integrate different data sources, GIS information, reality capture, and generally working with data science, data engineering, and a little bit of machine learning. And one more thing, if anybody is interested, we are having a hackathon together with Open Source Construction in the first weekend of February in Zurich Winter Tour. If you're interested in attending, just ping me on LinkedIn. We have some tickets that we can give you for free, so you can basically join us. And this is basically towards making everybody a developer. Every knowledge worker in the construction industry should become a developer because the industry is changing towards digital, and we want to make sure that also our industry has open source solutions and everybody have access to everything that they need. So, and we still have no questions. I think everybody is very, very happy with what you presented, and it was understandable.
I guess so. Yeah.
So,
I mean,
great.
yeah. If you don't have questions, we can end here if you do. I'm happy to answer.
Sure. I mean, from my side, I can only confirm what you said. Having a
Yeah,
single source of truth, optimization,
yeah,
having one plan
yeah,
instead of different versions of it
yeah,
will solve a lot of problems, and automation. Just automate
yeah,
everything that's repetitive.
yeah.
Yep. And with that, Milos, I want to thank you very much for accepting our invitation
Thank
and
you for inviting me.
for the great presentation. And keep on the good job. And I wish you and everybody at Programming Architecture a successful year. And everybody in the audience, you can find out more about Milos and his company on programmingarchitecture.com. Oh, we have a question now. So we have from Pierre. I would like to hear your opinion about cloud solutions and connected data coming from different programs. Are they reliable? For instance, Speckle, etc.
Yeah, I'm not so informed on like Speckle, SGJS, and so what they're doing. I mean, I am convinced that the way to go is that toward the cloud, because that's the only way like we can collaborate in real time. As far as I know, I mean, as far as I know, Speckle is still have a big challenge of making what they're doing user friendly. I think there are lots of people that are using that are very tech savvy and programmers and developers and so on, and they are trying to make it much more user friendly, and that's their challenge. I think the same challenge is the FCJS guys. So I can't talk about the use of this software because I don't use them, you know, but I can definitely say that they're on the right path. Like that's what I can say. What they are doing is developing systems of collaboration, right? So we are, and recently someone asked me that on LinkedIn, and I answered. I said we're climbing the same mountain, but from different sides. Like they are trying to solve the actual collaboration between people, but I'm trying to solve the automated generations of details, of screws, of threads, of this doing this repetitive work with workshop drawings and so on. So that's a kind of different set of problems, right? They're trying to solve like what if you have these models? How do you collaborate? How do you centralize that and so on? So in my way, I'm trying to integrate everything by using coding and programming, having this simple wireframe model and then extracting from it. And they're trying to be with their feet on the ground and trying to solve the problem as it is today. Like they create these connectors for Revit, for ArchiCAD, and try to push and pull. So maybe my thinking is a little bit more long term because what I'm developing is not so user friendly. So you need to ask specialists to do that for you. And their thinking is maybe a bit more short term. They're actually trying to bring that to the public. So in that sense, yeah, I mean, I fully support what they're doing. I just can't comment on how it works in practice because I myself do not use it.
Okay. Also, one sentence from my side, Pierre. Going to the cloud, uh, it is again perceived to be the evil uh, within our industry because everybody has problems with their data being published to the cloud and being accessible to everybody else. But I see no other way. I think it's inevitable that we all use cloud. Uh, uh, I don't know if you were into or are into rendering and creating a network of CPUs to be able to render, but scalable computing generally is much easier on the cloud because uh, you have unlimited resources and they are available on demand for you. And they are much cheaper than the normal physical resources. And the second point is accessibility, because if you have stuff in the cloud and on the edge, they are always accessible to you everywhere that you are, and you basically save a lot in the infrastructure, IT infrastructure costs, and you don't have to maintain your servers and stuff. So I think it's inevitable, and we see it in all the other industries. Uh, I can't imagine writing a new solution, writing a new platform without a cloud infrastructure, to be honest with you. Okay, then we have from Joro, any notions on AI and how it can be incorporated in the topics you are discussing?
Yeah, AI in the topics I am discussing, we're far from it. AI at the moment works on pixels, right, on images, text to images, and so on, but it doesn't work on spatial data because we don't have we don't have what to train it on, right? We don't have standardized 3D models in the same way we have standardized images. They're all JPEGs and they're all pixels, right? So that's also one thing that we could consider, that if we did bring some kind of standardization, IFC tried but didn't succeed really. If we did bring some kind of a standardization, then we could have AI that can be trained on spatial data, because that's for me the only one that's relevant, right? Right now, this is just a gimmick, right? You can generate different facades and different type of buildings, but who designs like that? Maybe only Zaha Hadid studio designs like that and starts from the shape and the form, but that's not the proper way for most architecture to be designed. So I think that there is some time until we can create different AI systems that can work on spatial data, because we need AI that can solve connections between beams and columns and work with space and 3D elements and so on. And I think we're still not there. Unless someone comes up with AI solutions that don't work on trained data, but somehow can think out of solutions without training, which is not impossible, but I don't see any evidence of it yet. That's the way we should go. We should try to standardize the 3D models in a way that can be used to train AI. We're not doing that yet.
Yeah, totally. I think one thing that might make sense with AI is whatever we do in programming is rule based, right?
Mhm.
So we as programmer have a set of rules, and we basically put it in the system and say,
Yeah.
if this happens, this should happen. If that happens, this should happen. And generally, optimization is mainly numerical optimization. So you go over it,
Yeah.
I don't know, a million times until you reach the best solution. So where I think AI can come into place is where you get rid of all the rules and say, these are everything that was built within the past decade. Train yourself, and now give me an answer. And
Yeah.
that's basically the trend that you see with machine learning,
Yeah.
with regenerative learning, with large language models. That's the way to go, to basically get rid of supervised classifications and rule-based models, and basically create a model based on a training data set, which then should include everything. But at the end, especially for construction, you have building codes in each country. You have 100,000 different dependencies on this design, and there you basically have to think about a validator of this generated result from the AI. But I'm with you. Until now, there is no spatial AI that I know of that handles topology, for instance,
Yeah.
well, or handles the graphs well. So then we have, yeah, thank you, Christian. Thank you, Pierre. which programming language you recommend for jobs we are discussing from Joro?
Well, the answer is always standard. I mean, I think if you don't have experience, you should start with Python. Everybody's starting with Python. It's easiest to learn. All the programs you offer scripting in Python. Not only AEC, all of them offer it. So that's the easiest way. And then it depends on the software you're using. I mean, as I said, I started with C++, but then stabilized on C# because Rhino was my main tool, and for Rhino it's the easiest to do. Consequently, accidentally, Revit also API is also in C#. RFM, which is what I use for static analysis, also has a C# API, so that kind of all fit well. But depends on what you want to do. If you want to develop plugins for Unreal Engine, then you might need to run blueprints or C#. But if you're a beginner, then it's kind of a no-brainer. You will start with Python, and that's it.
Exactly.
Yeah.
So again, I can only confirm Python is the way to go for starters, because you can start programming without knowing anything about object orientation, and that's the easiest way to start. But if you want to do some serious coding, then you either need to learn object-oriented programming in Python and continue there, or if you want something more performant, because Python lacks some performance features like parallel processing, like async processing. You can add libraries to it, but a different discussion for another day. Then you can basically go ahead with C#. I think you can't do anything wrong. If you want to go into web areas, I think JavaScript, TypeScript is also a really good alternative for it.
It's a must, yeah. For web, you have to go to JavaScript, of course, yeah.
Exactly. Or to generators. There are also some code generators that you can basically write your business logic, and then they generate your JavaScript. Not the same thing, but for starters, it's more than enough.
Okay.
So, any other questions?
I think I also have to go soon, so.
Okay. All right. Thank you very much, everybody who attended, and Milos, you especially. And if anybody had any questions, you can write it to me on direct messaging and LinkedIn, and I can ask Milos then afterwards.
Thank you very much. Keep doing what you're doing, and see you in the future.
You too.
Bye bye.
Take care. Bye.